Hello chemists and welcome to Bale's Chemistry. In this episode, I'm going to take a deeper look at the chemistry of weak acids. This is AQA specification 1.12, acids and bases, and it's examined on paper 1. If you haven't already subscribed to the channel, consider doing so to make sure you see the new videos released each week. We're very familiar with strong acids like hydrochloric acid and nitric acid. The reason why they're categorised as strong is the fact that they fully dissociate in solution. This means that the concentration of hydrogen ions is equal to the concentration of the acid. Weak acids like ethanoic acid and phosphoric acid are categorised as weak because they don't fully dissociate in water. This means that we have to use the acid dissociation constant Ka to calculate the concentration of hydrogen ions. The acid dissociation constant is a ratio between the complete acid molecules and the dissociated H plus and A-. Just like Kc, if the value of Ka is less than 1, then the equilibrium favours the left-hand side, and the concentration of hydrogen ions is lower. If the value of Ka is greater than 1, then the equilibrium favours the right-hand side, and the concentration of hydrogen ions will be much higher. Ka values are nearly always very small and well below 1, which means the equilibrium for these acids lie heavily to the left. When it comes to calculating Ka, we use this expression. It's just like Kc, with the products on the top being divided by the reactants on the bottom. To make these calculations easier to deal with, we make some assumptions. The first assumption is that in a simple solution containing just a weak acid, the concentration of H plus is equal to the concentration of A-, so we represent it as H plus squared. The second is that the concentration of HA remains the same at equilibrium as it was before the equilibrium, so it's unchanged. This is because very little of the acid dissociates, and making this assumption makes the calculations much easier to deal with. We're going to look at 3 examples of calculations where we try and calculate the 3 different values in the Ka equation. The simplest is to calculate Ka, where we use a standard Ka equation and swap out H plus and A- for H plus squared. In this example, we're asked to calculate Ka for a weak acid, which is a concentration of 0.5 moles per decimeter cubed and a hydrogen ion concentration of 0.2 moles per decimeter cubed. All we have to do is substitute the numbers and calculate the answer. The units for Ka are moles per decimeter cubed. To calculate H plus, we need to rearrange the standard Ka expression. I prefer not to add in the square root, but to save this as the final step. This is just my preference, and you may prefer to do it all in one go. With this example, we're given the values for concentration of acid and the value of Ka, and all we need to do is substitute in the numbers and perform the square root to arrive at the answer. It would not be uncommon for an exam question to go further than this calculation and ask you to work out the pH of the solution. In this final example, calculating the concentration of HA, we again need to rearrange the equation. This time we're given the values for H plus and Ka and can substitute them into our equation, remembering to square the concentration of H plus. These 3 different calculations are all simple enough, but you'll be unlikely to see them on their own in an exam question. This topic requires you to be able to perform many different functions and combine them when needed to solve different complex problems. One of these more complicated questions might be to work out the pH of a solution that remains after a weak acid has reacted with a strong base. When we react a weak acid and a strong base, the hydroxide ions will pull the hydrogen ions off the acid molecule, so it will react with more than just the dissociated H+, but reacts with the total concentration of the acid molecules. At the start of this calculation, we'll need to work out the moles of HA and the moles of hydroxide ions present. After the neutralisation reaction is complete, you'll be left with either an excess of acid or an excess of base. You can then work out the pH of the final solution using a similar method to the ones I've talked about in the previous episode on calculating pH. If we look at this example where 25 cm cubed of 0.1 mole per decimeter cubed ethanoic acid is reacted with 10 cm cubed of 0.2 mole per decimeter cubed sodium hydroxide, we can go through the steps at the top of that chain we've just looked at. We must first start by identifying the reactants in excess, and to do this we'll use a number of moles equals volume times concentration, remembering that our volumes are in centimetres cubed in the question, so we need to divide them by 1,000. We'll then calculate the number of moles of acid, and then the number of moles of base. We then look back at our equation and see that the reaction ratio is 1 to 1, so we can simply subtract the moles of base from the moles of acid, which shows an excess of acid by 0.5 times 10 to the minus 3 moles. In the next step, things get a bit more complicated. The maths is no more challenging, but it's the process which you must work through to arrive at the answer which is the hardest part to master. We've just worked out the excess of acid in the previous steps, and this is now the remaining HA. But we also need to work out how much A- was produced. This is the same as the starting moles of OH-. For every mole of OH reacted, it's produced 1 mole of A-. In the next step, we need to convert our number of moles into concentrations. To do this, we must first start off by adding the 2 volumes of solutions that we've added together, remembering to convert them to decimeters cubed. Dividing the number of moles by the volume will give us the concentration. First off with the HA, and then without A minus. This is an easily forgotten step because when we add two solutions together, we change their volumes and then we change their concentrations. Now we're going to use the Ka expression to calculate H+. We no longer make the assumption that H+ and A- are equal to each other, as the addition of the bases increase the amount of A- present in the solution. The final step is to calculate the pH using the minus log of hydrogen ions. Now, of course, there's a different route to take if there's an excess of base present in the solution after the reaction. The process is possibly a bit simpler. Instead of going back over the initial calculations, we'll start from after the reaction has taken place, where there's a 0.5 moles left over in the solution with a volume of 35 centimeters cubed. The first thing we'll do is we'll calculate the moles of OH, and that's simple, that's the excess, so that's 0.5 moles. And then we need to convert this into a concentration. So first we'll look at the whole volume and convert that into decimeters cubed, and then we'll do the number of moles divided by the volume to get the concentration of OH- left in solution. We're then going to use the Kw expression. We're going to rearrange it to have H+ as the subject, and then we're going to substitute in the numbers. Once we have the value for H+, we're simply going to do the same process as last time, where we use minus log of hydrogen ions to work out the pH, and end up with a pH of 12.1. Well, wow, that's it for this episode on weak acids. Those calculations at the end are super complex, but remember each step is something that you've done before and on its own is really quite simple. It's just putting them all into place and remembering all the steps along the way. If you found this video helpful, make sure you hit the thumbs up below, and thanks for taking the time to watch the video today.